shall we go? Hello my dear students, welcome to IMS GATE Academy. Good evening and namaskar. You are watching the most expected concept series of IMS GATE Academy. What is this series and what this series is all about, we have already discussed in lecture number 1. So we are through to this series, and in this series I am discussing the subject power electronics. So total 10 lectures will be there. So last lecture what we have discussed here is buck converter. So the buck converter is over right now, and I have obtained a very good response from you people. So today in this lecture I am going to discuss boost converter, another very important topic. Now the purpose of this series is to make you aware of all the important topics of this particular chapter, this particular subject power electronics, so that you will be able to score more when it comes to power electronics. So in this series, on the continuation, today I will be discussing boost converter. So without wasting the time, let's get started. So boost converter, okay. So this is the schedule that I have. We have discussed about the schedule in the last lecture as well. So you can see the schedule. Total 10 lectures will be there, and today it's time for the boost converter. The buck converter is also available in the playlist. You can just go and watch that particular lecture. So now boost converter. Now what is this boost converter, and what is the purpose of this, and why do you want to have the boost converter? See, when the available DC voltage is not up to the mark, means whatever voltage level we require, it is not exactly matching the same, and we need to step up the voltage for the application point of view, then we need boost converter. So the purpose of boost converter is to have fixed DC voltage at the input, and at the output we will be getting an output voltage which will be greater than the input voltage. So somehow it will be acting like an AC equivalent of a DC equivalent of an AC transformer. Like the way transformer does with the AC, it will be doing the same with the DC, and we can't use that AC transformer for DC, so that we have this circuit here, okay, that will be able to increase the level of the input voltage. Now why it is desired to have the boost converter? Because of the applications like solar application. You know, the voltage that we are getting from the solar panels is very low, and let us suppose that we have some application, for example the charging of the battery at the home, and so many other applications. If suppose we need to supply to the grid, in that case we need to level up, we need to increase the level of that input DC voltage, and that's why we need a converter. So boost converter will really help you out in this purpose. There are some other applications like satellite, okay, in that also we need to have boost converter. Like hybrid electric vehicle, in that also we need to have the boost converter, and a lot of home appliances, for that we also need to have boost converter. So all these applications require somehow DC to DC converter, whether it is buck converter or whether it is boost converter. In some application we need to convert the voltage at some lower level from the available battery voltage, and in some application it is desired to have a voltage level which is more than the available DC voltage. So the buck and boost converter find their application in a lot of areas. Now let us discuss specifically the boost converter, and this is one such topic from where you can expect at least 2 marks of gate question in the upcoming exam, okay. So what is a boost converter? So first of all, let me discuss with you a circuit diagram of the boost converter, and that is very important thing. All you need to know is about the circuit diagram, and rest of the things you will be able to derive very easily. This is the way we have done the things in buck converter. Same procedure we will be following in boost converter, okay. There also I told you, you need not to push yourself hard for remembering all the formulas. It is very easy, and you people have seen that. Similarly, we will be doing the things here as well. I will just let you know about the circuit, and we will discuss its working. We will analyze the circuit, and we will derive a lot of formulas as well. For that, just be there, okay. So what is the circuit of a boost converter? So in a boost converter, as we discussed, first of all we will be having a battery. First of all we will be having a fixed DC voltage, okay, a voltage of the battery Vs, and after that we will be having an inductor, okay, and now the switch will be connected in parallel. earlier the switch was present in series and inductor was part of the load side, but right now in boost converter inductor is part of the input side and the switch will be connected in parallel. Hello Nikhil Gaurav, welcome to IMS GATE Academy. So after that we will connect a diode. Okay, so earlier the diode was connected in parallel, now it will be connected in series in this manner. And after that we have the capacitor. Capacitor plays a very important role, as we have seen, in order to have a perfect DC at the output. And then finally we will be having the load. So this is the circuit diagram of a boost converter. This is the input voltage that we have, this will be the input current, and this is the inductor that we have. Now regarding inductor, what we will assume that this polarity of inductor voltage will be taken as reference polarity, and if it is carrying current in this direction, this will be considered as positive current. So this is regarding inductor. What do we have? Now this is the switch. This is the switch that we have. So this is our switch. Okay, it will be carrying a current which is called as the switch current. Now we have a diode here as well, and it will be carrying a current which is called as the diode current. Then finally we have a capacitor which will be carrying a current IC, and then we have the load RL where we want the output voltage, and this is the output current which has to be maintained constant throughout the operation, isn't it? This has to be maintained constant throughout the operation. Here is the load where we want the perfect DC output voltage, and capacitor plays a very important role in that. Okay, so in boost converter the inductor is present at the input side, the switch is there in the parallel, connected parallel, diode will be in series. As compared to the buck converter, the switch was there in series, inductor was at the load side, diode was connected in parallel, isn't it? So this is the circuit diagram of a boost converter, and this is very important thing. All you need to know, all you need to have is this particular circuit, and rest of the things you will be able to analyze very easily. How? Just see. So this is the circuit diagram of boost converter, and we have these essential elements connected here. Now before analyzing this circuit, let us discuss the assumptions that we are going to take here. So what are those assumptions? So the first assumption that we have is all the components of the circuit, all the components of the circuit are assumed to be ideal, are assumed to be ideal. Okay, all the components of the circuit are assumed to be ideal, means there is no loss. Okay, means there is no loss, and this is an idealistic approach, although there will be losses. Okay, so what we are assuming here is no losses. Okay, that means whatever is the power at the input, the same will be there at the output. No losses. Power input is equals to power output. Second important assumption that we are going to take is, the second assumption is related to the inductor current. And what is that assumption? The inductor current that we are assuming here for this analysis of the circuit is, the inductor current is assumed to be periodic. Inductor current is assumed to be periodic and continuous. Okay, so inductor current that we are assuming is periodic and continuous. What will happen in case of discontinuous conduction? We will have a different lecture for that. Okay, so what we have assumed here is that inductor current is assumed to be periodic and continuous. Now what do we mean by inductor current is periodic and continuous? Periodic means whatever value the inductor current is having initially, the same will be at the end of one cycle. So as far as inductor is concerned, you know that inductor will store energy for some time, and it has to release the same energy for the other time. It can't sustain with the energy, isn't it? So if it is doing so, what we will assume that inductor current is assumed to be periodic and continuous, and this can only, if this is the case, then we will be having one important condition, that inductor average voltage will be 0. average inductor voltage that we will be having will be 0. So this is regarding inductor. This assumption we will take care of while analyzing the circuit. Next important assumption that we have is related to capacitor, and that assumption says that capacitor average current is 0. Capacitor average current is 0. That means IC average that we will be having here is equal to 0. So what we will be having here, we will be having that IC average is equal to 0. There are two concepts related to inductor and capacitor in power electronics that you should have to take care of. In inductor, the inductor current is periodic, so the average inductor voltage is 0. In capacitor, the capacitor voltage is varying periodically, so the average capacitor current is 0. Okay, related to these I have discussed in more detail. Just go to the fundamental concept series of power electronics that I have taken in the month of May, and I will post the link of that particular series after this lecture in the comment box. So just go there and visit those lectures, and you will be able to analyze the inductor and capacitor behavior in power electronics. Okay, so IC average will be 0. The next assumption that we will be having is the capacitor. Again, it is related to capacitor. The capacitor is assumed to be very high. The capacitor is assumed to be very high. And why we are doing so? The capacitor is assumed to be very high so that the ripples in the output voltage will be minimized. Output voltage will be minimized. And if the ripples are minimized, we will be having the constant voltage at the output, which is desired, isn't it? Constant DC. For DC, the average and RMS values are equal to each other. Form factor is 1, ripple factor is 0. Okay, and that's the purpose of these filter circuit LNC. They are making this possible at the load end. Okay, so these are the important assumptions that will drive the operation of the circuit initially. Okay, now after that, let us see what will happen with the circuit during the on time. So during the on time, we will turn on the switch. We will turn on the switch and the diode will be off. That's what you will see around all the buck boost or buck boost converter. Once the switch is on, diode will be off. When the diode is on, the switch will be off. Both cannot conduct simultaneously. Okay, so during the on time means the switch is turned on. So we are going to turn on the switch, and we will be keeping the diode off right now. So switch is turned on. So when we will turn on the switch, just see here, the switch is on. So when the switch is on, what will happen to the diode? Diode will be off. Okay, diode will be turned off at that time. And this is the capacitor that we have, and this is the resistance that we have. Where do we want the output voltage? Now this current I0 has to be constant. This is the current, capacitor current. If it is flowing in this direction, will be assumed positive. So right now we are having diode off. Okay, the polarity of inductor will keep this diode off. Okay, so right now we have turned on the switch. And what is the polarity of this inductor voltage? This is the polarity of inductor voltage at the beginning. Okay, inductor current is flowing in this direction. This is the source current that we have, and this is the switch current that we have. And right now the diode current is not flowing, isn't it? It is 0 right now. So who will maintain this current I0? It is the responsibility of the capacitor. We will discuss when we will discuss specifically about the capacitor operation. Okay, so right now who is maintaining the output current? It is the capacitor. It will be discharging and maintaining the output current I0. So right now we are in this situation. Now if I apply KVL in this loop, okay, you can see here the load and source are disconnected from each other. So right now if we apply KVL in this particular loop, what we will be getting? So on applying KVL, just see here, on applying KVL, what we will obtain in this circuit, if I apply KVL, Vs minus VL equals to 0, or what we will be getting is VL equals to Vs. Let me call this equation number 1. So I have obtained this equation, VL is equals to Vs. Now, you know that VL we can also write it L DIL by dt, and this is equals to Vs. Or what I can write here is DIL by dt. This will be equals to Vs over L, isn't it? So DIL by dt. DIL by dt means rate of change of inductor current, also indicates the slope of inductor current. That means the inductor current is varying linearly, isn't it? And the slope that we have, this rate that we have is positive. This rate is positive. That means what we can refer from here is that the rate of change of inductor current, the rate of change of inductor current that we have is positive, isn't it? Rate of change of inductor current is positive. Is positive. So if it is positive, what it indicates? It indicates that the inductor current is varying linearly. Your content, delivery and confidence in explanation is truly awesome. Thank you, Nitin. So rate of change of inductor current is positive. That means the inductor current, rate of change of inductor current, DIL by dt, it indicates the slope as well. So that means inductor current is varying linearly. Okay, IL varies linearly. And this rate is positive, so it is increasing, isn't it? It is increasing linearly. And if the inductor current is increasing, that also ensures that L stores energy. Okay, L stores energy during that time. Okay, so when the switch is on, that always happens. When the switch is on, inductor current will increase linearly, inductor will store energy. Inductor will store energy. So this is what is happening when the switch is turned on and the diode is off. Let me call this to be the equation number 2 here. So this is exactly happening during the on time, T on. T on may be written as dt, where what is d? D is the duty cycle. You all know about that. Okay. Now what will happen when the switch is turned off? So this is what is happening during the on time. Now what will happen during the off period? Just see here. When the switch is off, so let me turn off the switch. So if I just turn off the switch, what will happen? So this is my inductor. Okay, now I am turning the switch off. So if the switch is turned off, okay, and let me draw the other elements of the circuit as well. So these are the other elements of the circuit that we have here. This is capacitor, and this is the output voltage we are getting at this inductor. I0 is maintained constant here. Okay, this is here ID. Okay, and this is the diode. Now diode will be on. Why this is on? See, we are turning off the switch. So we are turning off the switch here. So when the switch is turned off, if the switch that we have is turned off, at that time what will happen? If you see here, the inductor current is already flowing in this particular direction, yes or no? Now if suppose we have turned on the switch, this is the inductor polarity during the beginning, okay, in the on time. So if suppose the switch is turned off, then inductor current should have become 0, isn't it? And do you know the property of inductor? It cannot sustain that, it cannot bear that inductor current across it is changing suddenly. Inductor is in true love with the inductor current. So it cannot bear that the current across it is changing suddenly. So it will oppose that change. The energy that it has stored during the on period, it has to release that energy. It can't take that energy and go home. So it has to release that energy. How it is going to do that? It will change its polarity to show the opposition to this change. So what it will do? It will change its polarity. Right now inductor will change its polarity. So this will be the inductor polarity at the end. Okay, so let me only mark this polarity. So during the starting, the inductor has this polarity. This was the inductor polarity at the start. At the end it will be having this polarity. So this is the inductor polarity at beginning. Now inductor will be having this polarity at the end. Okay, let me mark this current, source current. This is what inductor current is. So this is exactly what is happening during the off period. So right now, when the switch is off, diode will be getting on. Can you see the polarity of the inductor? This is minus, this is plus this side. So this will make the diode in on condition. So whatever we have discussed is absolutely right. Conditions are in favor that the diode will turn on when the switch is off. So this is what is happening here. Now, if suppose we apply KVL here, so where we have to apply KVL? Just see here. If we want to apply KVL here, then we have to apply KVL in this loop. So in the outer loop, if we apply KVL, just see the path. In the outer loop, if we apply KVL, what we are going to get? So in the outer loop, if we apply KVL, on applying KVL, what we are going to get? On applying KVL, we will get Vs minus VL minus V naught equal to 0. While you are applying KVL, two polarities of inductors are available. So my suggestion will be always go with the reference polarity. Otherwise, if you are going with the new polarity that you have written here, then in order to that you have to take care of that it is negative. You have to learn, you have to remember that particular thing, that you are talking about inductor voltage and it is negative right now. So better to go with the reference polarity. That will give you exactly the same thing. So what will be the VL right now? VL will be Vs minus V naught, isn't it? Or what we can do, we can also write it V naught minus Vs, because we are designing boost converter and V naught is greater than Vs, isn't it? This is how you can do the things. So let me call this to be the equation number 3. Okay. Now what we have obtained here is that VL is equals to what? Vs minus V naught, and it is negative because V naught is greater than Vs. Okay. Or what I can write it? I can write it minus of V naught minus Vs. Now VL can be written as LdIL by dt, that is equals to minus of V naught minus Vs. Or what I can write here is dIL by dt, this is equals to minus of V naught minus VL by L. Let me call this equation number 4. Now what we can see from equation number 4 is that dIL by dt indicates the rate of change of inductor current, isn't it? And this rate what we are finding is negative. Negative, that means the slope is negative. Okay. So what we have seen earlier, rate of change of inductor current was positive. Here the rate of change of inductor current is negative, isn't it? So we can write that the rate of change of inductor current, that is IL, is negative here. So the rate of change of inductor current is negative. That means it is decreasing linearly. Okay, it is decreasing linearly. It represents a slope. It is decreasing linearly. And when the inductor current is decreasing, inductor might be releasing the energy. Inductor might be releasing the energy. And these are the things with the inductor and the capacitor. If they have taken the energy, they have to be returning the same energy, isn't it? These are the things with inductor and capacitor. So we obtain this condition. Okay. Now right now, what will happen to this capacitor? We will discuss the operation of capacitor in detail later in this lecture. Okay. So this is what is happening during the on time and during the off time. Now let us plot these things what we have obtained here. So when it comes to VL, how VL is varying? So in the on time, let me call this to be the on time. I am calling this to be T on, and let me call this to be the off time. I am calling this T off, and you know the total time is this. Okay. And what I can write it? I can write this to be dt only, and I can write this to be 1 minus dt. This is the off period. I can write it 1 minus dt only. So what happened with the inductor voltage? Inductor voltage during the on period is Vs, and during the off period it is Vs minus V naught, or V naught minus of V naught minus Vs. So it was Vs here, and it is Vs minus V naught here. Okay. So this is the inductor voltage that we have. Now what will happen to the inductor current? Inductor current, we have assumed that it is continuous. Okay, it is continuous, means it is having a value more than 0. It is not negative as well. Okay, so current is not getting discontinuous, it is continuous. We have assumed that inductor current is continuous and it is varying linearly, and during the on period it is increasing, during the off period it is decreasing. So for that changes, I have to show those changes like this. So it will be increasing during the on period and it will be decreasing during the off period. So it is increasing during the on period and it is decreasing during the off period. Okay, let me call this current to be the I minimum current. As it is continuous and it is varying linearly, I can assume that it is varying from certain minimum value to maximum value. So this is I minimum, and this value that we have will be I of maximum. Okay, and if I am talking about the average value of inductor current, this will be the average inductor current. So this will be average inductor current, IL average. Now what will be this value? As we know, this amount is called as the ripple current, del IL, which is equals to I of mx minus I of minimum. Means difference between maximum and minimum current is called as the ripple current. And how much will be this amount? If we are talking about this amount will be exactly half of this, del IL by 2. So this is how the inductor current is varying. It is increasing linearly for the on period and it is decreasing linearly for the off period. So during this time the slope is Vs by L, and during this time the slope is minus of V naught minus Vs over L. So this is how the inductor current is varying. For on time it is increasing linearly, for off time it is decreasing linearly, and we have assumed continuous conduction. And inductor current we have assumed as periodic. So you can see whatever is the value of inductor current during the starting, we are getting the same value at the end of one period. So it is periodic as well. It is periodic as well. Okay. So if the inductor current is assumed to be periodic, average inductor voltage is 0. Okay. Average inductor voltage is assumed to be 0. So now when we are talking about average inductor voltage is 0. Since inductor current is assumed to be periodic and continuous and it is showing the same pattern, the average inductor voltage that we will be having will be equal to 0. Okay. Now what do we mean by average inductor voltage? If suppose you have to calculate the average value of any quantity, this is how we will be doing. This is how we will be doing it. Now if I am equating it to 0, finally what I will be getting? I will be getting that inductor voltage, average inductor voltage will be 0. That means the area under the inductor voltage curve will be 0. So what is the area under the inductor voltage curve? So I am having these areas. This is the first area that I have. This is the second area that I have. Okay, so area under the inductor voltage curve will be 0. Now how to calculate the area under the inductor voltage? So for that we have Vs into T on, or T on I can write dt. So Vs into dt plus, how much is this? Vs minus V naught Vs minus V naught into 1 minus dt, and that we will equate it to 0, isn't it? What does that mean? That means the area under VL curve is 0, and that's exactly what we are doing here. Now let us solve this equation. So what we are going to get here? This will be Vs into d plus Vs 1 minus d minus V naught 1 minus d, and that will be equals to 0. Now from here we can see that we will be getting Vs into d, that will be cancelled. So Vs is equals to V naught 1 minus d, or what we will be getting here is V naught equals to Vs upon 1 minus d, and that is a very important relation that we have obtained in case of boost converter. This is how we will be getting the average output voltage of a boost converter. Okay. Let me call this equation number 5, and this is very important expression. Now as we know that d can vary from 0 to 1. D can always vary from 0 to 1. D can't be 0, D can't be 1. Neither we are going to permanent off neither the switch can be in permanent off condition, neither the switch can be in permanent on condition. So D can never be 0, D can never be 1. It will always be in between 0 to 1. Now if you are going to put D value in between 0 to 1, let us choose 0.5. If you are going to put 0.5 here, 1 minus 0.5 will be 0.5, Vs upon 0.5 will give you 2 Vs. So output voltage that you are getting is 2 times Vs. Means when D is varying from 0 to 1, we will be getting an output voltage always greater than the Vs. That means boost operation, or that means a step up converter. So we have stepped up the DC voltage. So that's how boost converter operates. It has stepped up the available input DC voltage, and that's a best possible way of getting an output voltage greater than the input voltage. So this is what this circuit has done for us. So inductor voltage and inductor current, how they are varying, what they are giving, we have already discussed this. Let me move to the next part, and which contains peak to peak ripple current. Let us discuss about it. Peak to peak ripple current. So this is how the inductor current is varying, isn't it? Now when we are talking about peak to peak ripple current, we are talking about del IL. Del IL means maximum minus minimum current. Maximum minus minimum current. So what will be del IL, ripple current? Let me talk about equation number 2, or you can also take equation number 4 as well. So let me take equation number 2. So what do we have from equation number 2? Just see. So equation number 2 has given us equation number 2, or we can take equation number, equation number 2. So equation number 2 is dIL by dt, which is equals to Vs upon L, and that we have obtained during the on time, isn't it? During the on time we have obtained that particular equation. So let me talk about equation number 2. So what do we have? We have dIL by dt, this is equals to Vs upon L, and that we have obtained during the on period, which is T on equals to dt. Okay, that we have obtained during the on period, which is T on equals to dt. Okay, so let me mark them here and remove from here. So now what we will be getting, just see here, dIL indicates the change in inductor current. So how much is the inductor current changing during the on period? So inductor current is changing del IL. So we can write here del IL. dt represent the change in the time. So how much is the time changing? Time is basically d of t during the on period. This will be equals to Vs upon L. Now finally what we will be getting? We will be getting del IL, and that will be equals to d Vs into t upon L, or what we can write here, that this will be equals to dVs upon FL, since we know that T is equals to 1 upon F. F is the switching frequency. So we have obtained a very important relation, and what is that relation? That relation is the peak to peak ripple current. The peak to peak ripple current, that is del IL. Now del IL is basically equals to what? Del IL is equals to dVs upon F into L, and that is a very important relation. This represents a very, very important relation. Okay, let me call this equation number 6. So many times we will be using this relation. So many times we will be using this relation. So del IL is what? Del IL is dVs upon FL. Now let me talk about what will be this average inductor current, IL average. What will be the inductor average current? If you see in the circuit, just analyze here. Whether it is on period, if it is an on period, inductor current is the same source current, isn't it? If it is the off period, again the inductor current is carrying the same source current. So whether it is on period or off period, inductor current and source current are always equals. If we are talking about the average inductor current, ultimately we are talking about the average source current. Yes or no? Do you agree with me? So ultimately we are talking about the average source current, isn't it? So average inductor current means nothing but the average source current. Yes or no? Average inductor current is nothing but the average source current. So how to find those? Okay, that will be the next topic. Okay, so let us discuss the power balance, and from here we will obtain the average source current. What is power balance? Power balance says that whatever we have at the input, the same power we will be having at the output, because we have simplified the things. We have assumed that all the components are ideal, so there are no losses. That means input power is exactly equals to output power, isn't it? So if it is so, what we can write here? We can write here that Vs into Is, that will be equals to V naught into I naught. Thank you Neha. So what we will get here, if suppose we want to get Is, that will be equals to V naught I naught divided by Vs. Now what is V naught upon Vs? V naught upon Vs, if we are talking about V naught upon Vs, we have derived one relation, and through that it will be 1 minus d, because we know that V naught is equals to Vs over 1 minus d. So what will be V naught upon Vs? That will be 1 upon 1 minus d, isn't it? So we have obtained this relation, and from this relation we can write average source current is equals to I naught upon 1 minus d. Wherever you have to find source average current, this is what is required. When you are applying power balance, you will be getting the average source current. So we have obtained right now the average source current. Okay, so we are one step away finding IL average. So what will be IL average? So guys, we are talking about average inductor current, and through the circuit what we have seen that this is nothing but the average source current, and whenever source current is to be found out, what we have to do? We have to apply the power balance, and through the power balance what we have seen that this is equals to I naught upon 1 minus d. Yes or no? This is equals to I naught upon 1 minus d. So this is a very important relation that we have obtained. Now if I analyze this particular relation, what I will be getting? IL average, what we have found out is I naught upon 1 minus d. Can't I write I naught to be V naught by R? So if I am writing it I know V naught by R, V naught, as you know, what is V naught? V naught I can write Vs upon 1 minus d. So that will be Vs upon 1 minus d square R. So these are very important relations that we have obtained. These are the very important relations that we have obtained. Let me write them in the box. IL average is basically nothing but I naught upon 1 minus d. We will be requiring this value, and I can also write IL average to be Vs over 1 minus d square into R. So these are the very important relations that we have obtained, isn't it? You just keep on analyzing the circuit, you will keep on getting number of expression. Don't waste your time in memorizing them, because we can analyze and we can have whatever is required. So why to waste our time? So see, we have an n number of relation. Let me call these equation number 7 here. Okay, let me call them equation number 7. So we have obtained what will be average inductor current. Okay, and we have also applied the power balance through which we have obtained this. Now let us calculate the maximum and the minimum value of inductor current. Okay, so from the circuit you can see, if you have to find out the maximum value of inductor current, that will be equals to what? That will be equals to, I can call this current to be average inductor current, and that we have found that this is equals to I naught upon 1 minus d. So I can write this current to be IL average plus, if I am adding this content, I will be getting IMX. So IL average plus del IL by 2. Now IL average I can write I naught upon 1 minus d plus, what is del IL? I can write it dVs upon FL. Just now I have derived the formula. If I can remember those formula, why can't you? Isn't it? That's as simple as that. So now finally what we can write for it? We can write it Vs upon 1 minus d square into R, and that will be dVs upon 2FL. So that will be the maximum value. Now no specific conclusion we can reach when it comes to IMX and IMIN. So let me keep it till this point. Now after that, if suppose I have to find what will be the minimum current, so I minimum, that will be equals to IL average minus of del IL by 2, isn't it? Looking into this waveform, if I have to find I minimum, that will be IL average minus this small portion. Now I will be getting the same formula. Here, but the difference is the minus will be there in between. So this will be the formula for finding the minimum value, and minimum value is very important for us. It's going to play a very critical role. So which number of equation this will be? I think this will be equation number 8 and 9. You just keep on counting the equations. So many equations we will be having here. Don't waste your time in memorizing them. So this is how we will find the minimum and maximum current. If suppose I have to calculate IL average, if these currents are known to us, I can calculate this by using this formula. This is also one of the formulas. IL average can be calculated by summing them up, okay, and taking the average. This is also I can find IL average. So now I have found out the current. Now questions may be there where you may be asked this current individually, their ratio might be asked, their difference might be asked, their summation might be asked, and number of ways possible through which the question can be asked from this particular topic. So I hope this is clear to everyone. Okay. So we have found out the current, we have applied the power balance, we have got this relation as well. Now let us talk about the capacitor. Okay, let us talk about the capacitor. So what will happen with the capacitor? Let me just draw the circuit again. Okay, so I have this circuit with me. Just see the circuit. So this was the circuit that I will be having. Now in this circuit, so this is the circuit that I have. Okay, what are the reference directions of the current? Don't turn on the switch, okay, let it only be the switch, and what will happen to the circuit we will observe. So this is the switch that we have, this is the diode that we have, and this is the inductor that we have. This is the inductor current, this is the source current, this is the source voltage, this is the switch and its current, and this will be the diode current, and this will be the capacitor current. This has to be the I naught, and this will be V naught across the load. If all the reference currents and voltages are like this, we will assume them positive, otherwise they will be negative, isn't it? So just see here, during the on time, what is happening in this circuit? What do we have during the on time? So during T on equals to dt. So during T on equals to dt, what do we have in this circuit? In this circuit we are having switch in the on position, but we have diode in the off position. Yes or no? So guys, when the diode will be off, okay, let me put the diode off. So when the diode will be off, let me move to the circuit that we have already drawn. Just see here. So when the diode is off, what is happening here? When the diode is off, I naught we have to maintain constant. So I naught we have to maintain constant. So who is maintaining I naught? Just see here in this circuit. In this circuit, what do we have right now? In this circuit, if I naught has to be maintained constant, then IC will be the current which will be maintaining I naught constant, and IC will be I naught. Means IC current, it will be flowing in this manner. So capacitor, it will be discharging, yes or no? So capacitor discharges itself to maintain this current I naught a constant one. Okay, so during off time, what will happen? Capacitor will discharge. Current IC will be equals to minus of I naught, and at that time capacitor discharges. Okay, capacitor discharges to maintain I naught constant. Yes or no? So at that time capacitor will be discharging and it will be maintaining the current I naught constant. Now what will happen during the off period? So during the off period, that is T off equals to 1 minus dt. So during the off period, what will happen in this circuit? During the off period, we will be having the switch in the off position, and we will be having the diode in the on position. Switch will be off, diode will be on. So if the switch is off, diode is on, what will happen next in the circuit? Just see. Again, just analyze this circuit. So if the diode is on, then we will be having here, what do we have? Here we will be having in this particular, and at this particular node we will be having I of L, or this is also I of D. This will be having IC plus I naught. Yes or no? This is the equation at that point of time. So when the diode is on, switch is off, what do we have? We have an equation in the circuit like this. Whether it is diode current, whether it is ID, diode current, or inductor current, that will be equals to IC plus I naught, isn't it? So earlier, when the diode was off, the load and source are disconnected. At that time, it is very difficult to maintain I naught. But who is maintaining I naught? The capacitor. Capacitor is discharging itself. The current across the capacitor is flowing in opposite direction just in order to maintain I naught constant. And at that time, IC is equals to minus of I naught. And capacitor is discharging to maintain the current I naught constant. Now it has discharged earlier. In order to sustain its energy, it has to charge again. And now we have, when the diode is on, load and source are get connected. So when the load and source are get connected, then capacitor can have ample scope to charge itself, isn't it? So what will happen? Now inductor current is coming into play, okay, and I naught has to be constant. I naught that we have to maintain is constant. So the capacitor inductor current, the part of the inductor current, who is taking that part? Capacitor will be taking that part, and it will use that into its charging. It will use that into its charging. And what will be IC? IC will be IL minus I naught. So this is how the capacitor will be behaving at. When during the on time, when the switch is off, switch is on, diode is off, at that time the load and source are disconnected. At that time, in order to maintain the constant I naught current, who is maintaining that? Capacitor discharges itself and maintains the current I naught constant. Now when the switch is on off position and diode is getting in off on condition, the discharge capacitor now have a chance to get itself charged. And through what it will be doing the same? It will be doing the same through the inductor current, isn't it? So it will take the part of inductor current, it will use it in charging, and I naught still remains constant. Okay, so this is how inductor capacitor current will be behaving. Now if we are going to plot these changes, what will happen? During the on time, that is dt, and this is during the off time, that is 1 minus dt. So during the on time, if you see, what is the value of capacitor current? It is I naught. So during the on time, the capacitor current is having a value which is I naught, minus of I naught. And what will be the capacitor current value during the on period, off period? It is IL minus I naught. So it will be like this. It will be like this. Okay, now again it will be varying like this. Okay, so this is how the capacitor current will be varying. What is this? This is IL minus I naught. Okay, this is IL minus I naught. So IL has maximum and minimum level. When you are subtracting I naught, this will not get 0. Okay, this will be above 0. So this is how you can understand it. So this is how the capacitor current is varying here. This is how the capacitor current is varying here. Okay, now as you know, capacitor current, there are some charges associated with the capacitor current. Always we will be having some charges associated with the capacitor current. Okay, so what will be that charge? So in order to find that particular charge, del Q, which is equals to C into del V, C into del V naught, that will be equals to the area, isn't it? Whenever you have to find the charge trapped in the IC current, you have to find the area. So what will be the area during this time? The area will be I naught into dt. The area will be I naught into dt, height into width. So I naught into dt will be the area. Okay, I naught into dt will be the area. Now if suppose I am calculating del of V naught here, what I will be getting? I will be getting I naught dt divided by C. So this is my del V naught. What is this del V naught? And which number of equation will be? I think this will be equation number. What could be the equation number here? Equation number 10. Wow, 10 equations we have derived. So this will be my equation number 10. And what it indicates? It indicates peak to peak output voltage, or ripple in output voltage. That will be the better thing to write. Ripple in output voltage. Okay, del V naught indicates ripple in output voltage, and practically this should not be there. This indicates the ripples in output voltage. This indicates the ripples in output voltage, and practically this should not be there. Okay, practically the ripples has to be minimized. And can you see one thing here? C is in the denominator. So if we have very high value of C, del V naught can be minimized, and that's why we have assumed in the assumption that capacitance should be taken of very high value, so that the ripples at the output voltage could be minimized. And you can see that thing, del V naught is inversely proportional to C. So if C we are taking very high, ripples in the output voltage could be minimized. Yes or no? So this is how we will obtain the expression of del V naught. Okay. So this is about the capacitor. So we have separately discussed capacitor. As I told you, each and every point, whether it is stated, unstated, whether it is hidden or it is obvious, I am not going to leave any point behind. Okay. So I have discussed each and every point, so that these concepts will be very clear to you, and you will be able to rock in the GATE exam. You will be able to solve all kind of GATE exam, whatever is being asked here. Let me move to the next point, switch current and diode current. So again, talking about the switch current and diode current, just see the inductor current. This is how the inductor current is behaving, isn't it? It is increasing from minimum to maximum and then maximum to minimum value for dt time and 1 minus dt times, on time and off time. Okay. Now guys, what is the switch current? So switch is getting on in the on period. When it is getting on, it is carrying the same inductor current, yes or no? When the switch is on, it is carrying the same inductor current. Let me show you that figure. So can you see here? We are talking about the switch current. So when the switch is on, it is carrying the same inductor current, yes or no? So when the switch is on, it is carrying the same inductor current, and when the switch is off, means diode is on. So diode is carrying the same inductor current during the off period, isn't it? So switch is carrying the same inductor current during the on period, diode is carrying the inductor current during the off period. So if we are talking about the switch current will have the same shape as the inductor current has during the on period, because inductor current during the on period is same, because the switch current during the on period is same as the inductor current. Switch is carrying the same inductor current during the on period. So this is how the inductor current will be varying, and this will be the average value. This will be the average switch current. Similarly, if we talk about diode current, diode is carrying a current, diode is carrying the same inductor current during the off period. So whatever is the shape of inductor current, just draw this particular shape during the off period. So during the on period, there is no inductor current. So during the on period, guys, there is no inductor current, and during the off period, the during the off period, the diode current is same as the inductor current. During the on period, there is no diode current, because diode was off during the on period. So this is how my diode current will be varying, and this is what I will call as the average diode current. This is what I will call as the average diode current. Now let us find the values of these. What will be the average value of switch current? So if we are talking about average switch current, can you see here? The switch is carrying current only during the on period, and it is the same inductor current. So this will be equals to what? This will be equals to D times the average inductor current, because switch current is the part of inductor current, and it is carrying that part only during the on period. So we can simply write this equation. Now what is IL average? When it comes to IL average, this is equals to I naught upon 1 minus D. So this will be the expression for average switch current. Whenever you have to find the average switch current, this is how you can find the average switch current. Now when it comes to average diode current, what will be average diode current? Just see here. So diode average current, that will be what? Now diode is carrying the same inductor current, but during the off period. So if I have to write this, I can write it off period is denoted by 1 minus D, and it is carrying the same inductor current. So this is how I can write the things. Now 1 minus D and IL average, I can put I naught upon 1 minus D. So that will get cancelled. So wow, what I have found out here is that ID average diode current is equals to what? Average diode current is equals to I naught. That's a really interesting thing that we have obtained here. Average diode current is equals to I naught. Average diode current is equals to I naught, and it has to be. See, diode current, if we are talking about, okay, this is equals to IC plus I naught at any time. If you are finding average diode current, that has to be average capacitor current plus I naught. Now what is this value? This is equals to 0. So any time if you want to find ID average, what it will be? At any time if you want to find IL average, ID average, what it will be? So ID average, it has to be I naught, and that's what we are getting through the formula as well. Okay, so this is how we can find the switch currents as well and diode current as well, isn't it? So we have calculated everything here. Now critical inductance, another very important thing, and so many times this has been asked in the GATE exam. Critical inductance, what it is? Critical inductance we have discussed in the last lecture as well. Now if you see in the last figure, inductor current is assumed to be continuous. Continuous inductor current means I minimum is always greater than 0. Okay, continuous inductor current means I minimum is always greater than 0. So if we are having the minimum value of inductor current 0, we are considering continuous conduction mode, that is CCM. Okay, continuous conduction mode, that is CCM. If I minimum is less than 0, means if it is negative, that means we are in discontinuous conduction mode. There is no doubt that we'll be having. It is a discontinuous mode. Okay, so if suppose we are talking about that I minimum is approximately reaching to 0, that we are calling as the boundary between continuous and discontinuous conduction. So that will be the boundary between continuous conduction mode and discontinuous conduction mode. I minimum reaching close to 0, that is the boundary between continuous and discontinuous conduction. So in order to get that particular current, we have assumed here that I minimum is 0, means the switch is operating at the boundary of continuous and discontinuous conduction. So what is this critical inductance? Inductance plays a very important role. Okay, the inductor is having the energy half of Li square. If L is having a significantly low value, it will not be able to sustain that energy for a long time. So the current may become discontinuous. Current may become discontinuous. So inductor has to have a value greater than a particular critical value, so that continuous conduction can be assured. Okay, so what is critical inductance? It is the minimum value of inductance for which the inductor current is at the boundary of CCM and DCM, that is continuous conduction and discontinuous conduction mode. So we are talking about boundary. So guys, if we are talking about boundary, if we are discussing about the boundary, that means I minimum has to be 0. Now what is I minimum? I minimum, if you have to write, that will be IL average minus del IL by 2, that has to be kept 0. Or what do we mean by that is that IL average, that has to be equals to del IL by 2. Now what is this IL average? IL average we have calculated, and this has found to be equals to what? This is equals to Vs upon 1 minus d square into R. And what is del IL? This is equals to dVs upon F into L, will become LC right now, critical inductance. So what we are going to get here? If we solve this expression, what we are going to get here is that L of C, this is equals to D 1 minus D square R by 2F, isn't it? This is going to be the expression for critical inductance, D1 minus D square R by 2F. So what we have obtained here is critical inductance is basically D1 minus D square R by 2F. If you remember, in case of buck converter, we have only 1 minus D R by 2F. Here we have D1 minus D square R by 2F. This is what we have here, okay? Now this is going to be equation number 11, I think. And this is a very, very important thing. This will be going to be the most important formula of the boost converter, okay? So we have calculated the critical inductance. Now if the circuit inductance is lower than this value, it is assured that you will be having discontinuous mode. So what we have to assure for continuous conduction, that's what we want. So continuous conduction, we have to take an inductance greater than this critical inductance value. Otherwise, we will not be able to assure the continuous conduction operation, okay? So that's what we have to do here, okay? That's what we have to do here. So this critical inductance we have calculated. Similarly, critical capacitance can also be found out. So for critical capacitance, we have to do the same thing, and that is V naught average. This has to be equals to del of V naught by 2, or we can also write del of Vc by 2. They are the same thing. V naught and Vc, capacitor and resistance, they are connected in parallel. V naught average is V naught, and what we have found as the value of del V naught. So just see del V naught, we have just calculated del V naught. How was del V naught? In capacitor current we have obtained this. So del V naught, yes, this is the del V naught, I naught dt upon C. I naught dt upon C. So we can write I naught dt upon C, and 2 is also there. Now this is V naught, and what we can write for here, V naught can also be V naught by R. D is D, T can be written 1 by F, and 2 and C are already there, and this C will become CC right now. So V naught and V naught get cancelled, and what will be CC? This will be equals to D upon 2RF. So this is the critical capacitance value, okay? This is the value of critical capacitance that we'll be having here, and that's it. This is how we have analyzed the operation of this boost converter. And what are the important formulas that we are having here? Let me have a quick look of those. So first important formula that we have is that average output voltage is Vs upon 1 minus D. And after that we have peak to peak ripple current. This is equals to D Vs over F into L. And after that what do we have is inductor average current. So average inductor current is basically the average source current as well, and this is equals to I naught upon 1 minus D, or finally we can write it Vs upon 1 minus D square into R. This is very popular expression. After that, what important formula we have derived? We have derived formulas for different current. So what was the switch current? Average switch current. Average switch current was D upon 1 minus D times the I naught, okay? And this is equals to D times IL average. This is how you can remember it, okay? This is how you can remember it. So average switch current, this will be equals to D times the IL average. Now when you are going to put the IL average, I naught upon 1 minus D, you are going to get this expression. Similarly, ID average, diode average current. Diode average current was equals to I naught. Okay, diode average current was equals to I naught. Apart from that, we have obtained the formula for critical inductance, and that is equals to D 1 minus D square R by 2F. And after that, we have found out the expression for CC, which is equals to D upon 2RF. So guys, these are the important formulas that we have. Okay. So all these are the average value. If suppose you want to calculate the RMS value, let us suppose that if suppose I want to calculate the RMS value of switch current. So average switch current, if suppose I have to calculate the average switch current, if suppose I have to calculate the RMS value of it, okay. So what will be the RMS value of this? For that I can write it under root d of IL RMS. Okay, and IL and IS are same current, so I can write it IS RMS. So this is also one way. Okay, if suppose we have to find the RMS value, under root d will be there, and you know how this is going to come from the formula of average and RMS value. We can get this value. Okay, so this is the end of boost converter, guys. So we have finished the analysis of boost converter. Now let us apply this into applications. Okay, just see this particular question of GATE 2019. Let us analyze whether we are able to solve the questions from whatever we have covered till now. Let's have a look. In a DC to DC boost converter, the duty ratio is controlled to regulate the output voltage at 48 volts. So what do we have? We have the output voltage. Just write the data, 48 volt. And after that, the input DC voltage. We have the input DC voltage, that is Vs, equals to 24 volt. The switching frequency is 50 kilohertz. So F we have is 50 kilohertz here. Assume ideal components and a very large filter capacitor so that the ripples will not be there. Ripple free operation. If ripple free operation is there, we set ourselves free. We are free to do the things. Okay, whatever we have done, we can simply apply those analysis. So that's fine. The converter operates at the boundary between continuous and discontinuous conduction. Okay, means I minimum is 0. Okay, it is neither in continuous nor in discontinuous, it is at the boundary of continuous and discontinuous conduction mode. The value of boost inductor will be, guys, what we have to find here is what will be the value of critical inductor, and given that the converter is operating at the boundary of continuous and discontinuous mode, this is the same situation in which we have derived the formula of LC. And what is the formula of LC? This is D 1 minus D square R by 2F, isn't it? D 1 minus D R is D 1 minus D square R by 2F. Now do we know the value of R here? No, we can't. We don't know the value of R here. Okay, and rest all the data are given. We don't know even the value of D as well. So for that, what needs to do? Just see here. We know that V naught is equals to Vs upon 1 minus D. So from here, 1 minus D will be Vs upon V naught. How much is Vs? It's 24. V naught, it's 48. So we will get 1 by 2. So 1 minus D is 1 by 2. So D will be 1 by 2. So we have obtained the value of duty ratio. Now how to get this R? So for that, power is given, isn't it? The output power is given to us. The output power is 120 watt. Okay, so in order to calculate the output power, this we can write V naught square divided by R. Okay, and this will be equals to 120. Since ripples are not there, we can assume that RMS and average values are equal. So V naught, that will be we required R naught here. So what will be R here? So R value that we will be getting from here will be V naught square divided by 120. How much is V naught? It's 48 square divided by 120. So from solving, you will be getting 19.2 ohms as the value of resistance. Now come back in this formula. D is 0.5. 1 minus D will also be 0.5. Square into R is 19.2 divided by frequency. Frequency that we have is 50 kilohertz. How much is going to be the answer? I think 24 microhenry. Is it correct? 24 microhenry. Will it be the answer? 24 microhenry. Will it be the answer? Let me check. Let us solve this equation, guys, and just check whether we are getting this answer. Whether we are getting this answer. So what do we have? We have 0.5. Just have a look whether we are getting the same answer. Yes, that's right. Okay, so that will be the answer. That is what we will be getting here. That is the right answer. So that's what we'll be getting here, 24 microhenry. So have we done anything else here? The formula that we have derived in the class, through that formula we are able to solve this question. This was a GATE 2019 question and it is carrying 2 marks. So can you see here how easily we have scored 2 marks? And the same scenario will be there in the 2024 exam as well. Okay. Now let me move to the next question. Just see this particular question. Consider the boost converter shown. So this is the boost converter shown to us. All the values are also given. Switch Q is operating at 25 kilohertz. So what is given to us? We have been given that the frequency is 25 hertz. So given that the frequency is 25 hertz. So the frequency is 25 hertz. That's fine. Not hertz, it's kilohertz. So the frequency given is 25 kilohertz. After that, duty cycle is 0.6. So D value that we have is 0.6 here. Fine. Assume the diode and switch to be ideal. That's absolutely fine. Under steady state condition, the average resistance seen by the source will be. So we have to find the average resistance. Okay. And now can you tell me average resistance will be equals to seen by the source will be source voltage divided by source current. Yes or no? Now source voltage is given to you. How much is it? It is 15 volt. We have to calculate IS. So what will be IS? So in order to calculate IS, you know is equals to I naught upon 1 minus D. Now do we know I naught? No, we don't know. Okay. We don't know the value of I naught. So we have to calculate I naught first. So what will be I naught? I naught will be V naught divided by R. Now what is V naught? V naught will be Vs upon 1 minus D since it is boost converter. Now do we have the values? Yes, do we have? Vs is 15, 1 minus D, this is 1 minus 0.6 and value of R is 10 ohm. So how much we will be getting here? 15 divided by 0.4 into 10. Isn't it? Duty cycle is given 0.6. So this is what we will be getting here. Yes or no guys? This is the boost converter that we have. So we will get the value of I naught. Is it correct? V naught upon R, Vs upon 1 minus D, that's fine, R, and this is how we will be getting the thing. So this will be equals to 15 divided by 4. Okay. Now come back here and put the values. 15 by 4 divided by 1 minus D. 1 minus D is 1 minus 0.6. So how much we will be getting? 15 divided by 4 into 0.4. That means 15 divided by 1.6. So we have the value of IS right now. Now in order to calculate the input resistance, which is Vs upon IS, what is Vs? Vs is given 15 divided by 15 upon 1.6. So we will be getting 1.6 ohm as answer, as easy as you can assume. This is how we will be able to solve this question, isn't it? Is there any difficulty that you have found in order to get the answer of this question? I don't think so, isn't it? Simply we have calculated this, and this is the part of GATE 2021 carrying 2 marks. So how easily you are getting 2 marks out of these topics, and this is going to be the scenario in the 2024 as well. In the year 2024 as well, you will be able to solve these questions. And guys, buck boost converter, DC to DC converter, they are going to give you at least 2 to 4 marks in the exam. So just attend these lectures and nobody can stop you scoring good marks in GATE. Now let's move to the next question. Just see this question, and this type of questions are repeated a lot of time. Now people used to say that GATE questions normally does not repeat. Yes, they are right, but it's the kind of detail, the data that we have is not going to repeat, but the type of question, the concept are repeated every time. Nobody is going to make new questions. Okay. So what has been said in this question? This was a part of GATE 2015. For the switching converter shown in the figure below, assume steady state operation. Also assume that the components are ideal and the inductor current is always positive, means it is continuous, and switching period is Ts. If the voltage is V, the duty cycle of the switch will be. So this is the converter given to us, and this is the boost converter that we have, isn't it? This is the boost converter that we have. Okay, this converter that we have is a boost converter. Now in this boost converter we have been given the average inductor voltage. Let me draw that voltage. let me again draw the voltage of inductor. So inductor voltage is given to us. Okay, and what is that voltage? The inductor voltage is given to us, and this voltage is having these levels. During the on period, see, this is the on period, it is 15 volt. So during the on period, it is 15 volt. During the off period, it is minus 45 volt. During the off period, it is minus 45 volts. So this is 15 volts and this is 45 volts. Okay, minus 45 volts. This is what is given to us. Now this time will be dt times and this time will be 1 minus dt of time. Okay. Now we know this is inductor voltage. Now we know that average inductor voltage across each converter will be 0. Average inductor voltage means we have to calculate the total area. This area plus this area will sum up to 0. So this area will be 15 into dt and this area will be minus of 45 1 minus dt. This is equals to 0. How much we are going to get? 15 into d, this will be equals to 45 1 minus d, or 45 minus 45d. This will come this side, it will become 60d, that will be equals to 45. So d will become 45 by 60, or we will be getting 0.75 as answer. We will be getting 0.75 as the duty ratio. Now this type of question we have also solved in buck converter. Now this is boost converter, we will be again solving the same question in buck boost converter as well. The kind of questions are getting repeated. Be prepared to apply this concept and you will get one gate question solved. Okay. Now see this question, this was a part of GATE 2017, and what has been said here, DC to DC boost converter as shown in the figure below is used to boost the voltage from 360 to 400 volt. Input and output voltage are given to us. Input voltage is 360 volt, output voltage is 400 volt. So input voltage and output voltage both are given to us. At a power of 4 kilowatt, input power, output power, whatever you can call, both are equal to each other, and this is 4 kilowatt because devices are assumed ideal. Fine. Considering continuous inductor current and continuous inductor current is also continuous, no discontinuous operation is there, that's fine. The RMS current in the solid state switch current we have to find, switch current. Okay, what we have to calculate? Switch current, and we have to calculate the RMS value. So RMS switch current will be under root d times the average inductor current. Sorry, not inductor current. First of all, in boost converter, you know, in boost converter, IL and IS are equal. They are the same current. So we can write here IS, isn't it? So this is what we need to do. Now whether D is given, D we can calculate. How we can calculate D? V0 upon Vs. This is equals to 1 upon 1 minus D, isn't it? So V0 is 400 divided by Vs is 360, and this will be 1 upon 1 minus D. So how much will be 1 minus D here? How much will be 1 minus D here? That will be 9 by 10. So what will be D? D will be 1 minus 9 by 10, that is 1 by 10, and that is 0.1. So D will be 0.1. So we have the value of D right now. Now what will be IS? Now what will be I of S? How to calculate I of S? So for that, power is given to us, isn't it? So IS we can calculate from P0 divided by Vs. How much is P0? P0 or PS, we can write PS here, not P0. P0 is given to us. How much is P0? PS is given 4 kilowatt. 4 into 10 to the power 3 divided by how much is Vs? It is 360. So what will be the value of IS? Just calculate. How much value of IS we will be getting here? This is 4000 divided by 360. So we will be getting 11.11 ampere. Now come back here. Under root of 0.1 into 11.11, how much it will be? 11.11 into under root of 0.1, and you will be getting 3.5 ampere as answer. This is what you have to do here. This simple analysis is required in order to solve this question. This simple analysis is required to solve this question. Now what's the problem? We can very easily solve this question, isn't it? Just see, everything is in front of you. Is there anything asked in a particular GATE exam that we didn't have discussed in this class? I don't think so, and the same I think will be with you. Okay. Now I have given you one quiz in last lecture related to buck converter. Have you solved that? If you are finding any problem, let us solve it together. So what has been given here is, in the chopper circuit shown in the figure, input DC voltage has a constant value 200 volt. So what is given to us? Input DC voltage is given 200 volt. The switch S is operated with a switching period of 40 milliseconds. So switching period is given 20 milliseconds. Fine. In such a way that conduction is at the boundary. Conduction is at the boundary means I minimum is 0. For V naught to be ripple free, output voltage is ripple free. We set ourselves free. We set ourselves free when it is given like that. The maximum value of inductor current will be what we have to find here. What will be the maximum value of inductor current? So let us analyze what is the problem. If suppose I have to find I max, then I max I can find with this equation IL average plus del IL by 2. And what do we have? It is a buck converter. So in buck converter, IL average is I naught and del IL means dVs upon FL. So that will be the formula. Now what do we not know here? What do we don't know here? We don't know the value of, we know the value of Vs, that's fine. Frequency we can calculate through this Ts. Okay, so if Ts is known, what could be the frequency? That will be 1 by Ts. Let us calculate frequency first. 20 milliseconds. So that will be equals to what? 1000 by 20. So that will be 500 Hertz. Isn't it? 1000, so 10 will cancel. We will be getting, that will be 50. So this is how we will obtain the frequency. So frequency we can calculate. You are the actual boost converter, sir. Thank you so much. Means you are getting boosted, and that's the purpose of this series. That's absolutely fine. Okay. So what we have to calculate here? Now frequency is known to us. Inductor is also given. Inductor we know. How much is the value of inductor? Inductor we are having 100 millihenry. Inductor is also known. We don't know the value of D. We don't know the value of I naught. Okay. So how to calculate the value of D? Okay. First of all, what we can do? I minimum we can write 0. I am writing I minimum to be 0. Why I minimum is 0? Because we have been given that we are operating at the boundary. Okay. So if we are operating at the boundary, this is the condition that we will be getting. Now I minimum 0 indicates that I naught or IL average this indicates that IL average, this will be equals to del IL by 2. Now I naught, IL average is basically I naught, del IL is D. See, we have written a wrong formula here, isn't it? We are talking about buck converter, but we have written a boost converter formula here. Okay, so don't mix up. This will be D 1 minus D Vs over FL. Okay, now the formula is right. So del IL, this is D 1 minus D Vs over FL. This is what we have. Okay. Now I naught, what we can write for I naught? I naught is V naught by R, or V naught we can write dVs upon R. So we can write it dVs upon R. That will be equals to D 1 minus dVs, and 1 by F I am writing T because T is given to us. Okay, and 2L. So from here dVs and dVs get cancelled. Okay, if I want to calculate 1 minus D I will be getting what? 1 minus d will be 2L over RT, or what I can write for d, d will be 1 minus 2L upon RT, isn't it? D will be 1 minus 2L upon RT. So you can memorize this formula. Whenever this condition is given, whenever we have I minimum equals to 0 in buck converter, we have this formula for D. D will be equals to 1 minus 2L upon RT. So we can directly apply this formula. So what will be the duty cycle right now? 1 minus 2L. L is how much? 100 millihenry divided by 2 into R. R is 10 ohm into T. T is given. T is 20 milliseconds. Okay. So now solve this equation. This get cancelled. This get cancelled, and we have 1 minus 1 by 2, that is we will be having 1 by 2. So D value that we will be having is 0.5 here. Now anything else is required, just see here what we don't have here. We are now having everything. I naught we can write dVs upon R, okay, plus D 1 minus D Vs upon 2 FL. Now put the values. D that we have is 0.5, Vs is how much? 200, okay, divided by R is 10 here, yes or no? And put the values here as well. 0.5 into 0.5 into 200 divided by 2 into what is F? F is 50, okay, and what is L? L is given 100 millihenry, okay. So now just solve this equation. Just solve this equation and tell me what we are going to get as an answer. You solve by your own, I am solving here. So how much we will be getting here? The value of this will be what? This we will get 10, okay. So definitely the answer has to be more than 10, and what we will be getting here, that's what we have to calculate, okay. So I am getting 10 here as well. So total answer will be 20. So that is the correct answer. Okay. So this is how we can solve this question as well. So this was the question. This was a quiz that I have given you in the last lecture. Okay. I hope you were able to solve. If not, you can refer to this solution. You can refer to this solution. So this is all from today's lecture. So right now we have completed the boost converter. The next topic will be buck boost converter. So buck is done, boost is done. Now the next topic will be buck boost converter. Next topic will be buck boost converter. Okay. So this is how, and this is going to be on the next Sunday from 6 to 8 p.m. So I will be waiting for you. Like the way we have done buck, like the way we have done boost, we will also analyze buck boost converter. Okay. So I will be waiting for you. I hope your people are liking this video, your people are liking this analysis, you people are liking this lecture, because the kind of response I am getting from your side, I am very happy. Okay. So keep on coming live on this class. If you are not able to watch live, keep on watching the recorded one. Okay. And I am very surprised, I am very happy with the response you people have given. Thank you so much. Thank you for attending this class. This is the end of this class. We will meet in the next class on Sunday. Okay, where we will discuss buck boost converter. So thank you everyone.